In this discussion, I'd like to finish up talking about the introductory section on sequences, which is going to involve some properties of these sequences which will be inherited from limits, a squeeze theorem. Both of these first two things are fairly concrete. Then there are some ideas that are somewhat more abstract than we're used to thinking about. Monotone sequences, because I have to be careful about that, bounded sequences, and we're going to find out that if a sequence is both monotone and bounded, it is convergent. If you have two sequences, AN and BN, both of which converge, that is, the limit as n tends to infinity of AN is some actual number m, as is the limit as n tends to infinity of Bn, then the usual things that you think should be true of limits are in fact true. The limit of a constant times An is the constant times the limit of the ANs. The limit of AN plus BN is the limit of AN plus the limit of BN. Likewise, for the difference, the limit of the product of AN and BN is the product of the limits, and the limit of a fraction is the fraction of the limits, the limit of AN divided by the limit of BN, assuming that the one on the bottom isn't zero. These are the usual kind of things that you expect out of limits, so this should come as no surprise to anyone. You do have to be careful that you're talking good sense, though. If AN is 5 plus n, then obviously the limit as n tends to infinity of AN doesn't exist, which we would write as equals plus infinity. The limit of the BNs, 6 minus n, also doesn't exist, but the limit of the sum does. If you think about having some individual AN plus BN, it's going to be 5 plus n added to 6 minus n, which is 11, and the limit as n tends to infinity of a constant, something that doesn't actually depend on the n, is the constant. So the limit of AN plus BN exists and is 11, even though the limits individually don't make any sense. So if you do the following, you're wrong. If you think of the limit as n tends to infinity of the quantity 5 plus n plus 6 minus n, if you break this up into the sum of two different limits, that's wrong. The reason that that's wrong is that property of limits requires that the two limits both actually exist as real numbers, not the infinity or negative infinity symbol. And of course, this is complete nonsense then. In Calculus 1, you had a squeeze theorem, and since these sequences are basically limits themselves, we're going to have a squeeze theorem for them as well. Suppose you had three sequences, AN, BN, and CN, and BN was always at least as big as AN, but BN is also never any bigger than CN. If the limit as n tends to infinity of AN and the limit as n tends to infinity of CN are the same number, L, then the limit as n tends to infinity of BN has to be L also. This is what we're going to call the squeeze theorem. The reason for this is not very hard to see. Bn is trapped between AN and CN, And as you allow the index n to become very big, both an and cn become close to L. And since bn is trapped between two numbers that are getting close to L, bn has to get close to L also. That's a very informal way of seeing this, but that is what's going on. As an example, I want to look at the limit as n tends to infinity sine n over n. To start off with, let me show you what not to do. This is wrong. This is totally wrong here. You think, I've got the limit of a fraction. So what I'll do is, I'll take the limit of the top divided by the limit of the bottom. This is wrong for two reasons. Reason number one, the limit on the bottom, which people would say equals plus infinity, that limit doesn't exist. A limit existing means that it equals an actual real number, not the infinity symbols. And even if that wasn't a problem, what about the limit as n tends to infinity of sine n? The graph of the sine function oscillates up and down between +1 and -1 for the y coordinates. Sine of something never settles down to anything. It doesn't converge, but it doesn't converge for a different reason than the other one. This one didn't exist basically because n blows up as you allow n to become large. This fails to converge, not for that reason, but because it continues to oscillate between -1 and +1. So this way of calculating is no good. And whatever you do, don't write sine of infinity divided by infinity, because that doesn't make sense. A much better way of going after this is to take advantage of how the top acts. Sine of n, no matter what n is, that's between -1 and +1. In an inequality, if you divide through by a positive number, you don't disturb the inequality any. So take this inequality and divide through by the number n, which is positive, and you get this inequality. As n becomes very big, 1 over n gets close to 0, and as n tends to infinity, -1 over n also tends to 0. So these sine n over n numbers are trapped between two numbers, both of which are approaching 0. That says that sine n over n must approach 0 as well. So we can actually figure out that this limit is 0 using the Squeeze theorem. We're going to have a behavior that some sequences exhibit called monotonicity, or having a monotone sequence. If A1 is bigger than or equal to A2, which is bigger than or equal to A3, and so on, or A1 is less than or equal to A2, which is less than or equal to A3, and so on, we say that the sequence in question is monotone. In this first case, as I increase the index, the A numbers either stay the same or get smaller. In this one, as I increase the index, the A numbers either stay the same or get bigger. How are we supposed to tell about this? One idea is to just do algebra. Write down an inequality that looks like this. Then solve that inequality and see for which n values it's true. If it turns out to be true for all relevant n values, then you've got yourself a monotone sequence. If it's false for all n, you also have a monotone sequence. If it's true or false beyond a certain particular index value, then you almost more or less have a monotone sequence. As we'll see later, in many cases, that would be good enough. What you don't want to see is this be true for a while, and then be false for a while, and then be true for a while, and have that continue. That would be undesirable behavior if you're trying to convince yourself that a given sequence is monotone. For example, I'm going to look at the sequence where a number n, a sub n, is 2n plus 1 over 3n plus 2. I want to think about what the next one on the list is going to be and try to figure out when, if ever, an plus 1 is less than an. And as we said on the previous page, this should tell me something about the monotonicity. We need to remember that these things are functions. The n is the thing that we're feeding into the function. So when we write this, what we mean is the way you figure out a number something is that you write down a fraction. Upstairs, it's going to be 2 times the something plus 1. Downstairs, 3 times the something plus 2. So if I want to figure out what a number n plus 1 is, the something is now n plus 1, not n. So I'm going to write this exact same formula down, except wherever I had n here, wherever I did something to n in that first equation, I'll do the same thing to n plus 1 instead. And after you simplify the algebra, you find out that a number n plus 1 is 2 times n plus 3 divided by 3 times n plus 5. So if I want this to be true, that means the same thing as wanting that to be true. At the moment, I have no clue if this ever happens, or always happens, or sometimes happens for certain n values, but not for others. At the moment, we have no clue. We're going to solve this inequality, and all I've got to remember is if I multiply both sides of an inequality by a positive number, then the inequality sign is undisturbed. You just leave it alone. The bottoms of the fractions, 3n plus 5 and 3n plus 2, are positive because n is at least 1. So if I take my inequality and multiply both sides by 3n plus 5 times 3n plus 2, I get an inequality that is equivalent to the one I started with. So if you cancel the denominators out, you find out that your original statement is equivalent to 2n plus 3 times 3n plus 2 is less than 2n plus 1 times 3n plus 5. Obviously, we can do the FOIL method or something on each side of the inequality, and after simplifying it, we found out that if we want the original inequality to be true, that's equivalent to 6n squared plus 13n plus 6 is less than 6n squared plus 13n plus 5. You can subtract the same quantity from both sides of an inequality without changing its meaning. So subtract 6n squared from both sides, and the 6n squares go away. Also, subtract 13n from both sides, and when everything is finally simplified, the original statement that a number n plus 1 is less than a number n, it turns out that that's equivalent to 6 is less than 5. This statement is false for all values of n because it's a false statement with constants in it. As a result, a number n plus 1 is less than a number n is never true. At first glance, that's kind of discouraging, but it really isn't. If this is never true, This must always be true. So it turns out that we have a monotone sequence after all. Another way to think about this is a variation on a theme of the f of x trick. We'll let f of x be a function so that an is f evaluated at n. If it turns out that f prime at x is negative, so the f function is decreasing over the relevant x values we're interested in, then that means that the a sub n's have to decrease also. If f prime of x is always positive for x bigger than or equal to 1, this means that in particular the ANs are increasing as well because they're function values for the f function. So this is another variation on a theme of a trick that we've used before. So let's look at that same sequence we were talking about before. Obviously, the easiest continuous function that I can cook up that will make f evaluated at n equal to a sub n is simply replace the n with x. And I'll use the quotient rule from calculus 1 to calculate the derivative. So I need to have the bottom times the derivative of the top, which is 2, minus the top times the derivative of the bottom, which is 3, divided by the square of what used to be on the bottom. Simplify the algebra, and it turns out that the derivative of f with respect to x is 1 over the square of 3x plus 1. 3x plus 1, looking only at x as being 1 or larger, is never 0. When you square something that's not 0, you get a positive number. So 1 over a positive number is a positive number, and I can guarantee you that f prime of x is always bigger than or equal to 0. In fact, it's always bigger than 0. That means the f function is always increasing, and since the a sub n's are particular cases of f values, the a sub n's have to increase as well. This is the same conclusion we got by doing algebra, but this time we used calculus instead. The other major idea is boundedness. A sequence is bounded if there are actual honest-to-goodness real numbers, none of this infinity symbol stuff, actual real numbers a and b, so that all of the a sub n numbers are between a and b. The one over on the left, we'll call that a lower bound for the sequence, and the b we'll call an upper bound for the sequence. If you draw the a sub n's on a number line, they are trapped between the number a and the number b. That's what bounded means. So think of the sequence a sub n equals 2 minus 1 over n, where n can be 1, 2, 3, and so on. As n gets bigger, 1 over n gets smaller, so I'm subtracting away smaller things from the 2. I think it's pretty clear that a sub n is always at least 1. On the other hand, I think it's also obvious that a sub n can never be more than 2.5. I'm being a little loose in my bounds here, but I think everybody can see what that means is all of the a sub n's lie within this interval. You could have bigger intervals. This interval is contained within the interval from 0 to 3. 0 to 3 would be a rougher, looser estimate for where all of these a numbers have to be. You can sometimes reduce the size of the interval you're looking at, but to make a bad pun, there are limits to how much you can do in that regard. So if you were much looser than you needed to be, it still would be true to say that all of the a sub n's lie between 0 and 3, but obviously this interval is bigger than it needs to be. If you're just concerned with getting bounds, though, 0 and 3 would work just as well as the bounds on the previous page. If you think about having the biggest possible lower bound, thinking about the calculations, 1 is a lower bound for the sequence, but if you push this even a little bit further to the right, you no longer will have a lower bound because you'll be to the right of a number 1 then. If you think about these numbers, 2 is obviously an upper bound for the sequence. But if you move even a little bit to the left of 2, if you make the n large enough, there'll be a sub n's 2 minus 1 over n, which would be to the right of your new upper bound. So the tightest interval that you're going to get, going from the biggest of all possible lower bounds to the smallest of all possible upper bounds, is going from 1 to 2. If I want to do calculation type things, looking at the sequence that we'd looked at previously, 2n plus 1 over 3n plus 2, if n is at least 1, then obviously both the top and the bottom of that fraction are positive. The ratio is obviously positive. It is impossible for 0 to be bigger than an. So we automatically have a lower bound. The upper bound is less clear. Sometimes we can do algebra methods. Other times we'll have to rely on other methods. I'm going to make a guess, though. I want to ask myself, can an ever be bigger than 5? Now, the answer to that question is going to be no, but to convince myself of it, I have to write this inequality down and convince myself that it doesn't have any solutions, at least in the range of n values that we're willing to use, which generically is 1, 2, 3, and so on. So write your inequality down. 3n plus 2 is positive. You can multiply both sides of the inequality by that positive number. Simplify. Simplify some more. Simplify some more. Negative 9 needs to be bigger than or equal to 13 times n. That means 13 times n has to be less than or equal to negative 9, and that never happens because n is positive. So this never happens, and if that never happens, that means that this always happens. 5 is an upper bound for the sequence. It is not the tightest upper bound, it's not the least upper bound, but it is an upper bound for the sequence. As a third variation on the f of x trick, suppose that you have on the interval from 1 to infinity a nice function f of x, and as usual f evaluated at n equals a number n. If this f function has a maximum or a minimum, or even sometimes a horizontal asymptote, we can sometimes figure things out about bounds for the a sub n. So I'm going to have my a sub n being 2n plus 1 over 3n plus 2. The f that goes with that is going to be 2x plus 1 over 3x plus 2, and I'm only interested in x's that include the n values that I'm interested in. So x bigger than or equal to 1. I want to see if this function has any maximums or minimums or long-term behavior or what? Calculate the derivative of f. After some work, it turns out to be 1 over the square of 3x plus 2. X is positive, 3x plus 2 is positive, 1 over 3x plus 2 squared is positive. The f function is increasing, at least on the interval of x values that we're interested in. Also, obviously, on that interval, the function's positive, so I know that 0 is a lower bound for the function f, and what I want to see is if I have any maximums or minimums or anything. The function is increasing. There is no place where f prime of x is 0. The top of the fraction would have to be 0. So the function is increasing, and it doesn't have any maximums or minimums. On the other hand, if you use L'Hopital's rule or the algebra manipulation, you'll find out that the limit as x tends to infinity of f of x is 2/3. So as x becomes very large, the y-coordinate on the graph, the f of x, gets very close to 2/3. But on the other hand, I know that the function f is increasing because of the derivative business. So loosely speaking, the f function looks like that. All f of x values in the interval from x equal 1 to infinity are less than 2/3. We already know they're all positive and they are increasing. So this tells me altogether that the function values for x bigger than or equal to 1 are between 0 and 2/3. But the f of x's are function values for a whole lot of x values, amongst which are the x equal n. So this fact tells me that 0 is less than or equal to an, which is less than or equal to 2/3. And we've figured out bounds both on the left and on the right for the sequence. Therefore, the sequence is bounded. We're going to use these two ideas, bounded and monotone, combined to figure out a fact that's very good to know about. Suppose you've got a sequence. The sequence is firstly bounded and also monotone. Then there's a conclusion that you can draw. The sequence converges. So bounded and monotone implies convergence. This is going to be a little strange because this is a binary yes-no type situation, converge or not converge. If it turns out that a given sequence is bounded and monotone, that tells me that it converges, but it doesn't tell me what it converges to exactly. So this is more on the level of a theoretical type of fact. I want to think about why this is. If you take math reasoning, you'll do a whole bunch of logical thinking along this line. It's not a bad place to start here. For simplicity, I'm going to think of a sequence where the individual sequence members, the A numbers, get steadily bigger as you increase the index. So A1 is going to be strictly less than A2, which is less than A3, which is less than A4, and so on and so forth. As n increases, the A sub n numbers go off to the right on the number line. I'm looking at less than rather than less than or equal to, just to dodge some unimportant technical details that would distract us. Suppose also that the sequence is bounded. which means it has both a lower bound and an upper bound. Out of all possible upper bounds, find the one that's as small as possible. I'm going to call that smallest upper bound L. So all of the a sub n's are less than or equal to L. Also, there can't be any number m which is less than L, so that all a sub n's are less than or equal to m. That can't happen. The reason for that is, if it did, then m would be an upper bound of the sequence, which is smaller than the smallest upper bound of the sequence, and that contradicts itself. Pick a positive number epsilon. Maybe it's big, maybe it's tiny, but it's positive. I claim that there has to be at least one of the a sub n's between L minus epsilon and L. The reason that that's true is, if it wasn't true, there would be no a numbers in here, no a sub n's in here. And if that were the case, all of the a n's would have to be to the left of L minus epsilon. That would mean that L minus epsilon is an upper bound for the sequence, which is smaller than the smallest upper bound, and that's a contradiction, which is why we said what we said a moment ago. Keep in mind what we've just said. Back up even a little bit, epsilon, and there has to be one of the a numbers in there. So back up a distance epsilon, one of the a sub n numbers has to be between L minus epsilon and L. Otherwise, we've got a lowest bound, an upper bound, sorry, that is smaller than the smallest upper bound. The distance between L and L minus epsilon is epsilon. So there is at least one of the a numbers that is within epsilon distance of L. On the other hand, if you look at any a sub n with an index bigger than this one, you're going to get a number that's bigger than a sub n because the a sub n's are increasing. It can't be any further, it can't go past the L, that is, because L wouldn't be a upper bound in that case. So after you've found this index capital N, all a sub n with little n bigger than this capital N have to be within this interval. In particular, all a sub little n with little n bigger than capital N are a distance less than epsilon away from this number L. So twist the language around until it matches up with the language we talked about previously. Given any positive number epsilon, there is a number capital N, so that if little n is bigger than or equal to capital N, then the distance between a little n and L is less than epsilon. This is literally the logical definition of what it means for the limit as n tends to infinity of a n to equal L. You can do something similar if the sequence is decreasing. You can include the possibilities where some of the successive a sub n numbers might be the same for a while. Those are picky technical details. In the end, you're going to come to the same conclusion. If you have a sequence that is both monotone and bounded, then that sequence converges to something, some actual real number. This business about bounded and monotone is a fact that's very important to us. We're going to use that fact to convince ourselves of a whole bunch of other things. Many of these things we can use to figure out whether infinite sums converge or not. So this is all for the sequence part. In the next discussion, we're going to begin adding things up, but we're not just going to add 4 or 5 or a million things up. We actually are going to stare the infinity right in the face, and we're going to add up an infinite number of things. You might think you can't get a finite answer out of that, but we'll see.